The next 3 segments will complete our journey to the modern periodic table, and all the stories take place at some point in the 1800s. Robert Boyle, Anton Lavoisier, and John Dalton all showed that the laws of the physical world simply will not yield themselves without painstaking, carefully measured experiments. But their work also demonstrated that the discovery process is not always that logical, systematic method that it's portrayed to be. No. Life and science don't always happen so neat and orderly. Sometimes it takes going in the opposite direction to actually make progress. What these men also showed us is that sometimes people just guess, or they accidentally stumble upon something. Sometimes they even nudge the data a bit to fit the hypothesis. This happens even today. Of course, this doesn't happen all the time, but if we were to admit it, it happens quite a bit, inside the laboratory and outside. Nevertheless, the pattern set by these early chemists set the pace for those who were about to follow. The periodic table was closer than ever, but what was needed was some way of separating out more of the elements. But how? Well, a new method was just around the corner. It was electricity, but a way was needed to reliably reproduce this mysterious energy. While conducting biology experiments with frogs, one man noticed that a frog's leg could be made to twitch with a spark of electricity, even if that leg was no longer attached to the frog. He was the Italian biologist Luigi Galvani, and being a biologist, he thought this was evidence that electricity came from an internal life force in the frog leg, which he called animal electricity. But another Italian, Alessandro Volta, wasn't so sure. He made experiments proving that animal electricity, even if it did exist, was unnecessary in order to make electricity. Volta left the frogs alone. Instead, he stacked up zinc and copper discs with a paper card sandwiched in between. Each card was soaked in salt water. When a wire was connected to the top zinc disc and another to the bottom copper disc, it produced a steady stream of electricity. No frogs needed. The bigger the pile, the more intense the shock he could produce. This was the first modern chemical battery, opening the world of electricity to practical applications, including chemistry. The debates between Galvani and Volta were among the most interesting in the history of science, because Galvani and Volta were actually good friends, and they disagreed often. These two were well known in their communities as outstanding scientists and gentlemen. In fact, Volta coined the term galvanism in honor of his friend Galvani, and the Volt was ultimately named in honor of and in memory of the gentleman from Italy, Alessandro Volta. Electricity ultimately became practical for the common man because of the work of the next 2 scientists, Sir Humphrey Davy and Michael Faraday. He was a science giant of the 1800s, and like Dalton, Sir Humphrey Davy was born in poverty and rose like a meteor in the chemistry movement of that century. Using Volta's battery, Davy discovered the elements calcium, strontium, barium, magnesium, and boron using a process called electrolysis, which we will look at in a moment. He was brilliant. He also discovered that nitrous oxide, commonly called laughing gas, was an excellent painkiller for medicinal use, and he proved that chlorine and iodine were elements. He invented the miner's safety lamp, saving many lives. He understood 7 languages and was an accomplished poet. He was knighted by the King of Great Britain and honored by Napoleon Bonaparte. He was the president of the Royal Society. He received many honors and awards in his career, and he published a book on fly fishing. Davy was an amazingly energetic and popular person in his day, a status which he completely reveled in. He also had a fairly irritable temper to add to his list of impressive accomplishments. Amazingly, his assistant, Michael Faraday, went on to become even more famous and influential than his mentor. Michael Faraday, the one-time assistant to Sir Humphrey Davy, went on to become one of the most beloved and influential scientists of all time. Many historians say he is the best experimentalist in the history of science. Because of Michael Faraday, electricity became practical for use by the common man and for use in industry. Electric motors, electromagnetic induction, electric current, and magnetism were all studied, developed, and their laws established by Michael Faraday. His personal assistants and close associates all commented that Faraday's character was one of gentleness and kindness. One biographer commented how Faraday was continually pressed to be the guest of the high and noble, but he would, if possible, decline, preferring to visit some poor sister in trouble, assisting her, take a cup of tea to her, or to read the Bible and pray with her. Faraday deeply believed in the unity of the Scripture and their historical accuracy. John Tyndall, the professor of physics at the Royal Institution of Great Britain, knew Faraday well and said of him, "Yes, it's true, but underneath his sweetness and tenderness was the heat of a volcano." Faraday was a man of excitable and fiery nature, but through high self-discipline he had converted the fire into a central glow and motive power of life, instead of permitting it to waste itself in useless passion. Faraday was not slow to anger, but he completely ruled his own spirit, and thus he captivated all hearts. Now, while it was his former employer, Sir Humphrey Davy, who was the pioneer in electrolysis, it was Michael Faraday who advanced the science and formulated the principles for electrolysis. And just what is electrolysis? Remember that Dalton thought that maybe atoms stayed together by means of little hooks? Well, many scientists were beginning to suspect that electricity had something to do with how atoms behaved. After all, it seemed plain to everyone that whatever else atoms were, they were all electrically neutral, meaning that whenever you touch a piece of iron or aluminum or a rock or water or anything else for that matter, do you get a shock? No, you don't. Unless, of course, there's a static buildup, and then you get a shock. But after the shock discharges, do you get shocked twice? No. See, everything seems to have a neutral electric charge about it. No shock. And if all the stuff was normally neutral, well, then that would probably mean that all the atoms or groups of atoms that made the stuff up were probably electrically neutral also. Neutral in the big things, neutral in the small things. Michael Faraday made it clear that electrical forces were in some way responsible for how atoms held together. It wasn't Velcro after all. Faraday, Davy, and others conducted experiments that looked something like this. Before we begin the actual experiment, we want to show that pure water is not very electrically conductive. Touching various items with the probes of this multimeter will help to demonstrate this. When touching metal or other conductive material, the multimeter completes a circuit and you can see the needle move. Iron, conductive. Aluminum, conductive. Wood, not conductive. Glass, not conductive. And pure distilled water, not conductive. Now, ordinary tap water will conduct some electricity because of the minerals dissolved in it. But if you add more minerals, like salt, it conducts electricity which we need for the experiment. Now the water completes the circuit and we can begin the actual experiment. Faraday made one of Volta's direct current batteries, very similar to our 9-volt battery. Now, you don't want to use AC household current on a water experiment like this. It can easily cause injuries, burns, and besides that, you will botch the experiment. Then he'd hook each side of the battery to a solid copper wire resting in the water. What is happening here? Bubbles are coming off each of the wires, lots off of one, and fewer off of the other. Through further experiments, Davy and Faraday realized that the bubbles were oxygen and hydrogen, which makes sense because we know that water, H2O, is made of hydrogen and oxygen. Somehow, the electricity was separating the bond that originally connected the atoms to one another. This clearly demonstrated that electricity was holding atoms to one another, and electricity was now separating them again. This method of separating the elements was called electrolysis, which literally means to electrically loosen. By holding a flame above one of the wires, the hydrogen will pop and fizzle, because hydrogen is also flammable. Eventually, scientists used more complex electrolysis methods and discovered new and exotic chemicals, all in a drive to separate out the elements. But the basic principle was nearly identical to the simple water electrolysis experiment. Electrolysis was responsible for the discovery of many elements in the 1800s. Faraday was one of the most well-known, influential, and highly respected scientists of his day. But he always said of himself, "I must remain plain Michael Faraday to the last." In some way, his character reminds us of Robert Boyle. During his lifetime, Faraday rejected a knighthood and twice refused to become president of the Royal Society. He was offered the privilege to be buried in the highly prestigious Westminster Abbey, where nearly all the kings and queens and aristocrats of England are buried. But in typical Faraday fashion, he politely declined. Faraday died in his home on August 25, 1867, at the age of 75. He was buried in his church's plot in London's amazing Highgate Cemetery. So, Boyle and Lavoisier established the foundations of chemistry, and Dalton finds that atoms do indeed weigh something, though something very small. And new methods, like electrolysis, are responsible for discovering more elements in that century, the 1800s, than in any other century in history. While all this was going on, the chief chemist at a London sugar factory was beginning to see certain distinct patterns in the physical properties of the elements. This was John Alexander Newlands, a chemist and a musician, and he noticed that just as the musical scale was ordered in periods of 7 notes, and then the 8th note repeated 1 octave up, so every 8th element was showing a similar repetition. Now, this was before the discovery of the noble gases, so Newland's idea looked something like this. and then sodium looked a lot like lithium. And then potassium looked and behaved a lot like lithium and sodium, and then it repeated. He even called this the law of octaves for chemistry. And in 1865, he presented these findings to the Chemical Society, and his observations and his work were, well, how shall we say, not favorably received. It just sounded too much like a return to the mysticism of the old alchemist days, and they pretty much ridiculed his work. In fact, one colleague asked Newlands if perhaps nature didn't categorize the elements alphabetically, since that made about as much sense as categorizing it musically. The Chemical Society denied publication of his work, and Newlands, along with his theory, was rejected. The truth was that Newlands was actually onto something, even more than he knew, and certainly something more than the Chemical Society knew at the time. But his system had certain flaws. To begin with, Newlands failed to leave any room in his system for the discovery of new elements. Plus, after element number 20, calcium, his system didn't really seem to work very smoothly. But amazingly, within 20 years, it became apparent to everybody that this repeating eighth element, minus the musical part, was actually true. And Newlands was the first person to discover the repeating periodic law. It took some pressure, but the Chemical Society decided to make some amends for their callous treatment of this insightful chemist. And they asked Newlands if he would present a lecture on the repeating periodic law, which he did. In fact, on the 100th anniversary of his death, the Royal Society of Chemistry formally recognized his insights and contribution to chemistry by placing this commemorative blue plaque on the wall of his birthplace in London. It reads, J.A.R. Newlands, 1837 to 1898, chemist and discoverer of the periodic law for the chemical elements, was born and raised here. Royal Society of Chemistry. If a periodic table is defined as ordering the elements to show periodic repetition of their properties, then in all reality, the credit for the first periodic table probably should go to the French geologist, Alexandre-Émile Bouguer de Chancourtois. Another French name that's fun to pronounce, Alexandre-Émile Bouguer de Chancourtois. He should get credit because just before Newlands published his paper, de Chancourtois took the then known elements, put them on a spiral graph, and wrapped them around a cylinder. Elements of similar properties lined up vertically and showed periodic repetition of their properties. Unfortunately, the diagram was published in a less widely read geology pamphlet, along with information on geology, which just wasn't very interesting to many in the chemistry field. It would take another 6 or 7 years before release of a publication that attracted worldwide attention and changed the course of scientific history. A few years after Newlands presented his findings to the Chemical Society in England, and after de Chancourtois devised his spiral cylinder in France, another scientist 2,000 miles away in Russia was also working with the problem of the elements. He was Dmitri Ivanovich Mendeleev, a man utterly engrossed in science, frequently to the exclusion of his personal appearance. He was often referred to as that wild Russian. There were stories that he would shave and have a haircut only once a year. One eyewitness reported that every hair on Mendeleev's head acted completely independent from the others. Physics and wild hair. It seems to come with the job. On long train rides, Mendeleev enjoyed playing the popular card game of solitaire, which back in Britain and Europe was called patience. Being a chemist, he invented his own game of chemical solitaire, using cards that he had made with the names and facts of all of the elements. Mendeleev spent hundreds of hours using various formulas and layouts trying to make sense of the elements. He wrote, "I began to look about and write down the elements with their atomic weights and typical properties on separate cards, and this soon convinced me that the properties of elements are in periodic dependence on their atomic weights." Like many before him, Mendeleev largely organized his periodic table by atomic weight. Yet Mendeleev succeeded where others did not, and we will find out why in a minute. But largely, this is how he played his chemical solitaire. He would play his cards in order of atomic weight, lightest to heaviest. Lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. And then it would repeat. Sort of reminds you of Newland's work, doesn't it? Mendeleev originally put his first cards in columns, but they eventually turned into rows like this. So that's how we will start it out for simplicity's sake. Also, Mendeleev left hydrogen out because it just wasn't quite fitting anywhere, typical of hydrogen. So for the time being, he set it aside. He also noticed that the valence of these 7 fit a pattern of 1, 2, 3, 4, and 4, 3, 2, 1. Lithium combines with 1 hydrogen or 1 other element. Carbon has a valence of 4 since it bonds with 4 hydrogen atoms and 4 carbon atoms too. More patterns. So far, so good. The next card, the 8th, is sodium. And sodium is a very soft reactive metal, just like lithium. And it has a valence of 1. So he put it right underneath lithium. More periodic repeating patterns. The next element was magnesium, which is a light metal, very much like beryllium above it, and with a valence of 2. So it went under beryllium. At this point, things were looking pretty periodic. The next heaviest element was aluminum, and although aluminum looks very different than pure boron, they both have a valence power of 3, so it went right underneath boron. Next was silicon, then phosphorus, sulfur, and chlorine. Chlorine obviously fits because it's a gas like fluorine above it. And even though phosphorus and sulfur weren't gases like the elements above them, the similarity was, once again, the bonding powers. The next card was potassium, a soft, very reactive metal, usually kept safely out of the air by being submerged in mineral oil. It also has a valence of 1, just like lithium and sodium. Calcium is a soft metal acting very much like beryllium and magnesium, with a valence of 2. Things were looking good up until calcium, number 20, and that's when the trouble began. In fact, if you remember, that's where Newlands found his trouble, at calcium, number 20. Titanium was the next known heaviest element, and it should have gone underneath aluminum since that was the next place. But to Mendeleev, it actually had more in common with silicon, including the same valence. So Mendeleev did something very bold. In fact, in virtually any article or book you read about Mendeleev, This is one of the favorite words they use about him, bold. They say that Mendeleev was very bold because he left a blank card underneath aluminum, predicting that there was a missing element yet to be discovered that belonged there. In fact, he boldly did this a total of 3 times. And what's more, he boldly predicted what their weights would be and what their general composition would be. This boldness revealed that Mendeleev thought he had discovered and not invented the periodic table. Had he thought he was inventing the periodic table, he may not have left the gaps in there and tried to shoehorn all the elements into a preconceived pattern. Mendeleev thought that he had discovered a fundamental pattern in nature which had yet to be completed. He predicted that this missing element would someday be discovered and have a weight of 44, and that these two would be discovered sometime after he was long gone, and they would have the weights of 68 and 72. He was right and he was wrong. He was right that these elements were eventually discovered, and that they did indeed have the very weights and characteristics that he boldly predicted. Scandium, gallium, and germanium. But Mendeleev was wrong that they would be discovered after he was long gone. In fact, it was only a few years after his prediction that scientists discovered those 3 elements. And it was this fact, the discovery of 3 boldly predicted elements, that rocketed Mendeleev into scientific fame and forever linked his name with the periodic table of the elements, an association which Mendeleev encouraged, by the way. Now, to be completely fair, at the same time Mendeleev was working on his table in Russia, 1,000 miles to the west, the German chemist Lothar Meyer published a table of the elements virtually identical to Mendeleev's. It was so close and came out at nearly the same time that a rather bitter dispute developed between Meyer and Mendeleev for many years. You see, in 1860, while Abraham Lincoln was campaigning in the United States to be president, chemists from all over Europe met in Karlsruhe, Germany for the very first International Chemistry Conference. One of the main topics was how to accurately calculate atomic weights, and 2 of the scientists sitting in the audience were none other than Dmitri Mendeleev and Julius Lothar Meyer. Both men were capable chemists. Both had independently worked for the famous chemist Robert Bunsen, who developed the famous Bunsen burner, and both were now sitting in on this important international conference taking notes. Armed with new and improved scientific data, scientists all over the world raced back home, hoping to be the first to develop a better periodic table of the elements. Lothar Meyer and Dmitri Mendeleev won that race. In 1882, both men were presented the prestigious Davy Medal by the Royal Society for outstanding scientific achievement in chemistry, though Mendeleev was clearly considered to have primacy, and both men knew it. When awarded with the medal, Mendeleev simply rose and bowed, not feeling comfortable with addressing the audience in English. In fact, he never even introduced himself. He was so uncomfortable. Lothar Meyer then stood and, being the gentleman that he was, graciously introduced them both, saying, "I am not Dmitri Mendeleev. I am Lothar Meyer." The audience gave a thunderous standing ovation for both scientists. So if they were so close, why does Mendeleev get top billing? Well, Mendeleev was pretty feisty in just about every area regarding chemistry, and apparently just about every area of life, for that matter. He didn't believe in a lot of things that scientists believed in at the time. He didn't believe the atom could be divided any further. He didn't believe in the electron when it was discovered a few years later. And he didn't believe the noble gases were real when they were discovered. He didn't believe in radioactivity when it was first discovered. In fact, Mendeleev fought nearly every new discovery in chemistry from the time that he developed his periodic table. He was almost hyper-conservative in his science, except one time when he boldly predicted the future discovery and characteristics of 3 missing elements in his periodic table. Now, Meyer left blank spaces in his periodic table, but he never went so far as to boldly predict the characteristics of those missing elements. And this one successful and uncharacteristic prediction of Mendeleev is why he edged forward and why Mendeleev is considered the father of the periodic table and not Lothar Meyer. In all, Mendeleev published some 30 periodic tables and designed 30 more in manuscript form that were never published. You can see that Mendeleev's periodic table looked quite a bit different from our modern periodic table because several important discoveries were yet to come that would shape the modern table. Very few Russian scientists since have matched Mendeleev's worldwide recognition. He had a fairly acidic personality, and his private life was about as wild as his hair. He was very involved and outspoken with Russian politics, but his popularity kept him from anything harsher than official rebukes. His first marriage was a complete disaster, ending in divorce. And then he fell obsessively in love with and married a young art student named Anna Popova. Unfortunately, the laws of the Russian Orthodox Church required a 7-year wait before you could remarry. And of course, Dmitri didn't want to wait and was married by bribing a local clergyman with about $400, a clergyman who was later defrocked. So, legally, Mendeleev then had 2 wives, and that caused quite a stir. But again, he was so popular that the new Russian Tsar, Alexander III, had to give a personal ruling and stated that Mendeleev has 2 wives, yes, but I have only one Mendeleev. In later life, Mendeleev hired a balloonist to ascend 2 miles above the cloud cover so he could better observe the 1887 solar eclipse. Unfortunately, the balloon lacked power to launch both Mendeleev and the experienced balloonist. As the eclipse was fast approaching, Mendeleev tossed out the balloonist and launched out by himself. Having no prior experience in ballooning, he made no attempt to control the balloon until after the eclipse was done, after which time he somehow managed a landing. His name and wildly bearded face were instantly recognized by every Russian at the time. He was a meteorologist, an author, father, economist, and art critic. Mendeleev was widely honored by scientific organizations all over the world. This large impact crater on the far side of the moon is called the Mendeleev crater, and radioactive element 101, mendelevium, was named in honor of him. In 1907, Dmitri Mendeleev, the father of the periodic table, died peacefully reading a copy of Jules Verne's Journey to the North Pole. He was 72, and at the time he was seriously contemplating a journey to the North Pole using another balloon. Students from the university carried large copies of his periodic table at the funeral procession.